Welcome to another module in this massive open online course on probability and random variables for wireless communication. In the previous module, we had seen the concept of a random variable, the random variable x, the concept of a probability density function for this random variable x, and we had looked at the exponential random variable x. Let us now look at the relevance of this concept, or the relevance of this concept of a random variable, specifically the exponential random variable in the context of wireless communication. So, let us now look at an example, simple example from the context of wireless communication. So, let us look at a simple example, because remember this is a course in probability and random variables, the applications of probability and random variables and random process in communications, especially wireless communications. So, let us consider a typical wireless communication scenario with a transmitter and receiver, a cellular scenario in which a base station is transmitting to a mobile. So, for instance, I have a typical wireless scenario, and we have already seen this to some extent, a wireless transmitter which is transmitting. So, I have my base station which is transmitting to the mobile. This is my mobile, and therefore, there is going to be a direct line of sight path. However, there are also going to be several non-line of sight paths between the base station and the mobile, which arise from the presence of what are known as scatterers, right. So, we have a line of sight path and several non-line of sight paths. So, we are looking at a wireless communication environment, correct. So, in a wireless communication environment, we have a transmitter and a receiver. There is no dedicated medium, or there is no guided propagation medium between the transmitter and receiver. Therefore, there is a signal that is radiated into the space by the transmitter. This propagates along a direct line of sight path from the base station to that mobile. So, there is a line of sight which is also represented by the nomenclature LOS, which stands for line of sight. So, this LOS, this stands for line of sight, and there are several obstacles such as, for instance, trees and buildings in the propagation path. These are known as, these obstacles here, these buildings, trees, etc., these are known as scatterers. These are known as scatterers, which basically scatter the transmitted signal. So, from these scattered scatterers, there are several scattered signal components or several reflected signal components, which also, so these deflect the signal, that is the transmitted wireless signal, and the deflected signal components also arrive at the mobile. So, there is one line of sight, and there are several non-line of sight, which is denoted by NLOS, several non-line of sight components which are deflected or which are scattered by the scatterers such as trees and buildings, which also arrive at the mobile. So, this NLOS stands for non-line of sight, and as a result of this, what is going to happen over here, these several signal components, these are going to cause interference, these interfere. So, these are going to cause interference at, so these multiple signal components, so these multiple signal components cause interference at the mobile receiver. As a result of this, the received signal quantity, the interference can be constructive or the interference can be destructive. As a result of this, the received signal quality or the received signal level is random in nature. This is known as the fading channel, because the received signal power is fading, and therefore, the received signal power is random in nature. So, interference. So, in the wireless channel we have the sequence that we said is we have multipath propagation, this multipath propagation leads to, what does this lead to? Multipath propagation leads to interference, leads to multiple signal components, which leads to interference. So, multiple signal components. These multiple signal components in turn lead to interference. This is known as multipath interference. This leads to interference, and because of interference the received signal is fading. So, this leads to a fading signal. This leads to a fading signal, and as the signal is fading, the fading signal, the received power, therefore, the received signal level or received signal power is random. The received signal power is random in nature. So, there is multipath propagation arising because of the scatterers or reflectors in the wireless environment, that leads to several non-line of sight components. These non-line of sight components together with the line of sight components, when they impinge on the mobile, they cause interference between these multiple components, between these multiple signal components. The interference can be constructive or destructive depending on the amplitudes and phases of these different signal components, and therefore, the received signal power is fading, that is, the received signal power at the mobile is random, is fading in nature, it is varying with time, correct, and therefore, the received signal power is random in nature. In the fading, this wireless channel is a fading wireless channel, the received signal power is random in nature, and the power of the channel coefficient, the power of the fading channel is characterized by the probability density function. Therefore, the fading power, the power of the fading channel, which is denoted by G, let us say we denote the power of the fading channel by G. This is characterized by the fading channel distribution. This is characterized by the probability. This is random, as we said, the received signal power is random. This is characterized by the exponential probability density function e to the power of minus G for G greater than or equal to 0, which is basically nothing but, as we have seen in the previous module, this is the exponential probability density function. What is this? This is the exponential, PDF with parameter A is equal to 1. So, this is a very interesting example from wireless communication, an application of the probability theory that we have learned so far in wireless communication. We have said that the fading channel is random in nature, that is the signal level and hence the power level in the fading wireless channel, because of the unpredictable nature of interference arising from these random scatterers in the environment. The signal power is random in nature. This signal power, if we denote this power of the fading channel coefficient by G, G is a random variable. The probability density function f of G is denoted by e raised to the power minus G for G greater than or equal to 0, because it is a fading power, the power cannot be negative. So, this probability density function is defined only for G greater than or equal to 0. This is characterized by e raised to minus g, which we are saying is the exponential probability density function. Remember, in the previous module we had seen the exponential probability density function, which is basically the exponential probability density function is a parametric distribution which is a e to the power of minus ag. If we set a equals 1, then we get basically what we get is e to the power of minus g for G greater than or equal to 0. So, therefore, what we are saying is in a fading wireless channel, the power is distributed as an exponential random variable with the parameter a equal to 1, and this example is about specific fading wireless channel which is known as the Rayleigh fading wireless channel. This is valid for a specific wireless channel which is known as the Rayleigh fading, which is a very popular model for wireless channel. This is known as a Rayleigh. This is known as a Rayleigh fading channel, in which the amplitude of the fading coefficient is distributed as a Rayleigh fading channel. So, we are looking at a fading wireless channel. We are saying that the amplitude of the channel coefficient of this random channel coefficient is distributed as a Rayleigh fading channel. The power is distributed as an power which is the square of the amplitude is distributed as an exponential random variable e to the power of minus g with parameter which is an exponential probability density function with the parameter a equals 1. And therefore, this probability density function can now be used to answer several interesting questions. For instance, we can use this to characterize the behavior of the wireless channel. So, we can now use this probability density function very interestingly, we can use this probability density function to characterize the behavior and properties of the behavior and properties of the wireless channel. We can use this to characterize the behavior and properties of the wireless channel. For instance, let us look at this simple example. Since we are talking about the characterization of the behavior of the wireless channel, let us look at this simple example. Let us consider this Rayleigh fading wireless scenario that we are considering so far, and let us ask the question, what is the probability that the attenuation of the wireless channel, that is the signal attenuation of the wireless channel is worse than that is, we are asking the question, what is the probability, that is, given this fading wireless channel in which the power is distributed as an exponential random variable, what is the probability that the attenuation of this fading wireless channel is worse than 20 dB. That is, if I transmit a signal x of t with a certain power p, the received signal power is 20 dB attenuated with respect to the transmitted signal power. What is the probability that the attenuation of the signal, of the wireless signal, is worse than 20 dB? And we can answer this as follows. The answer to this is as follows. Since the attenuation, the power attenuation, the dB attenuation has to be since the attenuation is 20 dB, the dB attenuation has to be less than, or the amplification or the power gain has to be less than or equal to minus 20 dB, which implies 10 log 10 of G is less than or equal to minus 20 dB. Remember, the power gain is G, the power gain is in dB is 10 log to the base 10 of G, and for attenuation to be worse than 20 dB, this has to be less than or equal to minus 20. So, 10 log to the base 10 of G is less than or equal to minus 20, which implies, which basically implies that G is less than or equal to 10 to the power of minus 2 is equal to 0.01. And we already know that G is greater than or equal to 0, because this is the power gain, power cannot be negative, which means we are asking what is the probability that 0 is less than or equal to G is less than or equal to 0.1. So, the probability that the attenuation is worse than 20 dB is the probability that the power gain of the wireless channel G lies in 0 to is greater than or equal to 0, but less than or equal to 0.1, which means it belongs to the interval 0 to 0.1. So, this is the same as the probability, it belongs to 0 to 0.01. What we are saying is, this is the probability that attenuation, this is equal to the probability that attenuation is worse than 20 dB, and the probability that this belongs to 0 to 0.01, this is nothing but the probability G belongs to the interval 0 to 0.01. Remember, the probability that any random variable belongs to a particular interval a to b is integral a to b integral 0 to 0.01 integral of the probability density function, which is f of g dg. We already know that this probability density function f of g is distributed as the exponential random variable with parameter 1. So, this is integral 0 to 0.01 e to the power of minus g dg, that is the probability that it lies in the interval 0 to 0.01 is the integral of the probability density function e to the power of minus g between these limits 0 to 0.01, which is basically nothing but integral of e to the power of minus g is minus e to the power of g evaluated between the limit 0 to 0.01, which is basically, you can verify that this is 1 minus e power minus 0.01. Now, I am going to use an approximation for small x, e to the power of minus x is approximately equal to 1 minus e to the power of minus x. Therefore, this probability is approximately 1 minus 0.01, which is equal to 0.01, and therefore, probability that attenuation is worse than the probability that the attenuation of the wireless channel is worse than 20 dB, or the probability that the gain G is less than equal to 10 to the power of minus 2, that is 0.01, is approximately 0.01. Therefore, the probability that the attenuation is worse than 20 dB of the fading wireless channel is worse than 20 dB is 0.01, or a 1% chance that the received wireless signal is attenuated by more than 20 dB. So, this probability attenuation of fading wireless channel that attenuation of fading wireless channel is worse than 20 dB is 0.01, or basically there is a 1% chance of attenuation chance of attenuation being worse than 20 dB. So, this is a practical example in the context of wireless communication. We have said that the wireless channel is fading in nature. We said that this can be characterized by an exponential random variable with parameter a equals 1, and we said this can be used to characterize the behavior of the wireless channel, and we did a simple example in which we found what is the probability that the attenuation, that is the attenuation of the received signal, is lower than minus 20 dB. So, we will stop this module here. We will continue with other aspects in the subsequent modules. Thank you very much.